All right, so let's talk a little bit more and let's stop. We produce a couple of examples. Let's make them slightly more concrete. Let's put the names. So this last example, which are elements, so these are n by n matrices preserved in some form. Well, we made somehow the distinction between GLV and GLN. So let's make that distinction here. So if B is this quadratic form into K, but we pick a basis for V. So picking a basis for V is choose such an isomorphism. Then B gets B is now a matrix form. Representing that bilinear form. So people usually write something like this. So if you have some B of U, V of V, W, where these guys are row vectors in Kn, then this is, let's say, V transpose times B times W, and now this guy is the matrix representing this bilinear form. So once you choose bases everywhere, then this condition of preserving, where did I write it down? Where did I write it down? Oh, here it is. This condition of preserving the bilinear form gets translated into the following thing. So now O, B, N is the set of n by n matrices with entries in the ground field such that, well, A transpose B plus BA is equal to 0. So this starts to sound like what you may have seen for SON, for example. So let's give some examples. First of all, if you take by B the identity matrix, then this is just A transpose plus A is equal to 0. And this is what you usually call SON. So let's put some names. So let's see. Let's think keep in the back of your head for a second. This is going to work for any field, but keep in the back of your head for a second that K is the complex numbers. So let's try to think on V being finite dimensional, and B being non-degenerate. Something like the determinant of this matrix being non-zero. Then we can think of two examples. We can ask that B is skew-symmetric so let's call this guy C. So this is B of VW plus B of WV is equal to 0. Or let's call this other example B and D is when B is symmetric. So this is B of VW minus B of WV is equal to 0. So let's deal with example C first. So what does it mean to have a non-degenerate skew-symmetric bilinear form on a finite dimensional complex vector space? then just pick V is going to be K 2L. To have a non-degenerate skew-symmetric bilinear form on a complex finite dimensional vector space, the vector space has to have even dimension, and then the bilinear form can be put in this matrix. 0. And here I is, well, let's put it here. This is an L by L matrix. And this is an L by L matrix. And this is the 0 matrix, the 0 L by L matrix. So the corresponding Lie algebra in this case, that's why I'm calling, see, this is C, the Lie algebra, O, B, N, which in this case is 2L. It's called CL, and it's also called SP2L, and it's called the symplectic Lie algebra. So this gives us infinitely many Lie algebras, one for each L. There's another series, which I'm now calling examples B and D. Let's divide those. So what does it mean to have a symmetric bilinear form which is non-degenerate on a complex vector space? Well, I'll give two different examples. Example B is going to be the following. We'll have the following. So let's say this is going to depend whether or not our vector space is odd dimensional or is even dimensional. So if V is K to the 2L plus 1, then we'll take the matrix for the bilinear form to be of the following form. We'll put a 1 here, 0, 0. So this is an arrow 0 and 0. Here now we have a 2L by 2L matrix, and inside of here we'll take I, 0, 0, I. And the other example, so this is going to be the example BL. And the example DL will be when V is K 2L, and now B is the same thing. Now this is even dimensional, so we can just take I, 0, 0. So this gives us two different series, BL and DL. So we have a series which is BL, CL, DL. For every value of L, we have these three series of Lie algebras. These two series of examples are called orthogonal Lie algebras. So this is SO 2L plus 1. This is called SO 2L. Then we have SP2L. And we had also constructed already SL L for every little L. So we have these four series of Lie algebras. Later we'll find out a few more exceptional cases over the complex numbers. But let me mention a few more examples inside of GL that are already there. So inside of matrices, we've seen GLN, and we have all these four series of examples inside of GLN. There are more examples that are easy to construct. So for example, inside of here, let me construct three of them. TN, DN, and let's say UN. UN is a bad name. Let's call it NN. So we have, let's say, Tn is inside of GLN the set of upper triangular matrices. Dn the set of diagonal matrices. And Nn the set of strictly upper triangular matrices. Check that these three are Lie algebras. The bracket of two upper triangular matrices is again an upper triangular matrix. Actually, you know better than that. So, I mean, there's a bunch of examples that you can find, but the bracket of two upper triangular matrices is not only upper triangular, but it's strictly upper triangular matrix. Check that that's equal, actually. Okay. So these are more examples. Okay, so now let's move on a little bit to something I am interested in. And a whole bunch of mathematicians are interested in representation theory of Lie algebras. Does that come from? Well, for any vector space, GL of that vector space is a Lie algebra. In particular, G, if you give me a Lie algebra, GL of G is again a Lie algebra. So if G is a Lie algebra, GL of G is a Lie algebra. And we have a Lie algebra morphism between G and GL of G. It's called the adjoint morphism. So how does it go? Well, for any A in G, you give me at A. This should be an endomorphism inside of G. So at A acting on B is by definition the bracket of A and B. Lemma, this is a morphism of Lie algebras. So for that we need to check, well, first of all, that this map is linear. That I leave to you. This is just the fact that the bracket is bilinear, so in particular it's linear in the first argument. But let's check that it preserves the bracket. So we need to check that the adjoint of A and B, we want to check that this, let's see how it acts on C. We would like to check that this is the same thing as the bracket of the adjoint of A. Well, what we want to check is that the adjoint of the bracket is the bracket of the adjoints. This we want to check. In order to check this inside of GLG, just apply it to two vectors C. I mean, this is an equality inside of GLG. In particular, if this is true for every C in G, then this is going to be true in GLG. Okay, but now this, by definition, this is A, B, bracket and C. Now, where does this bracket come from? This is the bracket inside of GLG. So this is the adjoint of A composed with the adjoint of B acting on C minus the adjoint of B composed with the adjoint of A acting on C. And now, well, let's just apply again the definition. This is the adjoint of A acting on BC, but the adjoint of A, this is just taking the bracket with respect to A, minus, well, now it's just A and B switched. And this is the Jacobi identity, or some form of it. Yes, I probably moved this side to that side. This is an example of what's called a representation of a Lie algebra. This is called the adjoint representation. Definition. Definition. A representation of a Lie algebra G on a vector space V is a Lie algebra morphism from G into GLV. Now, typically, especially during this class, we will be working with the dimension of G being finite, but we may have the dimension of V being infinite. Namely, there are interesting infinite dimensional representations of finite dimensional Lie algebras. In particular, every Lie algebra has a nice representation, which is the adjoint representation, GLG. Now, you may ask, is it true that every Lie algebra is a subalgebra of GLN for some n? Because if that's the case, then, well, the study of Lie algebras is just the study of matrices with the bracket that is just this A times B minus B times A. And a good starting point to start looking for such a case, well, if this is an embedding, for example, right? So suppose we have a representation and that this is a monomorphism, a one-to-one map. Then we can just look at the image of G inside of here, and that's a presentation of G as a subspace of matrices. And we have such an example already. We have a representation from G to GLG. Now, is this guy a monomorphism? That's not true. For example, if G is abelian, then the adjoint representation, what's the image of such a guy? Every guy here goes to an endomorphism that acts by 0. So it's a very, very hard question, the question of whether or not any Lie algebra is a subalgebra of the space of matrices. And somehow it's in your homework. But we can say a few words about that, actually. Let's continue. Yeah, let's give a couple more of definitions. So let's look at this. Z of G, this is going to be called the center of G. This is a set of all A in G such that A and B is equal to 0 for every B in G. So that's the center of G. But in particular, given this definition of the adjoint representation, what do we see? Well, any guy in the center gets mapped to the 0 morphism. For any b, this guy is going to be 0. On the other hand, if I have an endomorphism here that comes in this way, I mean, it's certainly going to be in the kernel. So if I look at the kernel of this morphism, I claim that's a center. But this tells us a lot, because, I mean, this already gives us something non-trivial. First of all, the center is an ideal inside of G. Because we have a morphism of Lie algebras, the kernel of a morphism is an ideal inside of the source. So the center of G inside of G is an ideal. And if you remember the definition of any simple object for groups and so forth, let's see. So let me give a definition. A Lie algebra G is called simple. We'll revise this later. F, there are no non-trivial ideals properly included in G. But in particular, if you have a simple Lie algebra, well, then we already know that the center has to be 0, because the center is an ideal. But if the center is 0, then that guy has 0 kernel, and G sits inside of GLG. So any simple ideal, any simple Lie algebra is a linear Lie algebra. So what we proved linear Lie algebra here means a subalgebra of GLN for some n. Again, the proof of this is, well, if we have no ideals, no non-trivial ideals, this center has to be 0. That means the kernel of that map has to be 0. And just the adjoint representation gives us an example, an embedding. All right. That's as much as I want to say. Let me just mention, perhaps, now that I mentioned what representations are, let me see a few that we've seen already. A nice property of the one-dimensional Lie algebra is that K with the bracket 0 is also GL1 of K. So elements of the ground field also are the same thing as 1 by 1 matrices with the entries in K. So in particular, a character of G are the same thing as one-dimensional representations of G. Remember, characters were maps from, preserving the brackets, from G into the one-dimensional Lie algebra, which of course is the same thing as GL1 because there are abelian Lie algebras anyways. So in particular, we already have a bunch of representations of GLN because we know that just take alpha times the trace is a representation of GLN for any alpha in the ground field. So now we can produce some representations. Okay, so let's give some more. I mean, let's check a couple of them. And then we'll go back to producing more examples of Lie algebras. So let me give a representation of GLN, which is kind of the one that you should be expecting, that is the following. So I'll say the following. GLV acts on V. This means there's a representation of GLV on V. What can this be? Well, a representation of a Lie algebra is, by definition, a map from the Lie algebra into GL of the vector space. So I'm looking for a map from GLV into GLV. Just take the identity. Check that this is a map of Lie algebras. And that's it. So we have a representation. So, which a priori is kind of interesting because here in GLV we have a natural guy, which is the bracket. So we have matrices with their bracket here. And how do they act on V? Well, they just act by, they are endomorphisms of V. So I can just act by A acting on V. All right, so that's as much as the representation I want to talk today. By the end of the class, we should know some nice properties of representation. We should be able to characterize finite dimensional representations and by characters and so forth. Most of this class is going to be two things. It's going to be classifying simple finite dimensional Lie algebras over the complex numbers and then trying to understand their highest weight representations. Okay, so we know what a one-dimensional Lie algebra is. Let me do two more things today. Let's classify two-dimensional Lie algebras. Let's say G is a two-dimensional Lie algebra. What are the possible scenarios for G? Well, an obvious one is it can be abelian. So one example is suppose it's abelian. So now let's suppose that it's not abelian. Okay, so let's classify all possible two-dimensional Lie algebras that are not abelian. Okay, so consider, so if it's not abelian, there exists, let's write that down. So, assume G is not abelian. There exist A and B inside of G, not zero, that are linearly independent. Such that this bracket is not zero. So let's call this bracket C. Okay, so let's see. We can probably give this as an exercise. Actually, yeah, I don't want to go into this because I think I assigned this as an exercise. So I should check my own website, but I think I assigned you as an exercise to check that this is isomorphic you can rescale A and B so that A with B is equal to B. And if I didn't assign you this, then tomorrow I'll prove it. But I think somehow this was in the exercise. And this is just a matter of rescaling. But there are two-dimensional algebras, two non-isomorphic ones. One is abelian, and the one that is non-abelian is this one. It has two generators, such that the bracket of A with B is equal to B. Okay, let's produce many more Lie algebras. So far, essentially most of the Lie algebras that we produced are inside of GLD that come from symmetries of some certain, we'll see this later, certain groups acting on a vector space. But anyhow, they have to do with symmetries on V. In particular, this matrix is acting on a vector space V. So now we'll produce some other ones that have to do with vector fields on a manifold. The algebra, I say that I don't want to talk about geometry, so I'll just give you an algebraic perspective to this, which is the following. Say A is an associative algebra. Actually, we don't need associative to what I'm going to say now. So if you want, you can just remove this guy. But a definition, a derivation of A is an endomorphism D such that D of AB is equal to dA times B plus A times dB for every A and B in the algebra. You don't need this guy to be actually associative. This is true for, this is the definition for any algebra. The thing is that if A was a Lie algebra, then this definition would read as follows. It would read that D of AB is the bracket of dA with B plus A times the bracket of dB. Plus the bracket of A with dB. So that's the derivation. In particular, we've seen examples of derivations of Lie algebras. So, lemma add A is a derivation of G for every G, for every A. So these are called inner derivations. Now, let's move back to the derivations of an associative algebra. So, for example, in the case where the associative algebra is, so if A is the algebra of functions, on a manifold, you can think of smooth functions, say C infinity functions, on a manifold M, or analytic functions, or whatever they are, the algebra of derivations of those guys are vector fields. There's an algebraic way of thinking of vector fields. Just give me the algebra of functions, and derivations of those are vector fields. Vector fields act by derivations from functions. They satisfy this equality here, that I think you call them Leibniz rule. All right, so the set of all derivations of A, now it's an associative algebra, or if you want a Lie algebra as well, or Lie, is called, is denoted, not called, is denoted der A theorem, der A is a Lie algebra. Actually, it's a subalgebra. Well, derivations are by definition endomorphisms of the algebra A. And endomorphisms form a Lie algebra. You already know this. So it's a Lie subalgebra of those. So this is the... So we're going to have now the algebraic version, but the proof is the same, that the bracket of vector fields is again a vector field. So let's check this. I mean, the fact that it's a linear subspace is obvious. This condition here is linear. If I just take linear combinations of these guys, this equation here is linear indeed. So the fact that derivations form a linear subspace inside of endomorphism is obvious. Let's check that the bracket is preserved. So we have D and D prime inside of derivations of A. Well, so let's check the bracket. So we want to check that the bracket acting on A and B, we want to check that the bracket is still a derivation. So let's do this. The bracket is inside of GLA. So this by definition is D acting on D prime on AB minus D prime acting on D on AB. But now D prime is a derivation, so this is the same thing as D acting on D prime A times B. Let's be careful. Plus A times D prime B. So that's just this guy. Minus D prime acting on dA times B plus A times dB. And now D is a derivation. So this is D prime A times B plus D prime A dB. So that takes care of this guy. Plus dA D prime B plus A dd prime B. That takes care of that other guy. Now let's go here. Minus. Well, this is going to go to that part of the board, and this is going to be horrible. Anyhow, let's finish. D prime dA times B minus dA D prime B. That takes care of this guy. And let's finish somewhere. This is going to be quite bad. Okay, let's finish this sequence on this side. So we have minus d prime A dB minus A d prime dB. Okay, so what do we want to check? So what we just did is we just took the bracket on this, and now we want to check whether or not this was a derivation. So I want to check if this is equal to, so the question is that guy equal to the bracket of D with D prime on A times B plus A times the bracket of D with D prime on B? If that's true, then that'll be the fact that we have a derivation for the bracket is a derivation. Well, let's expand this side now. So this is D prime minus D prime D on A times B. So that's this guy. Plus A D prime minus D prime D on B. So I want to check that this is equal to this. Well, the only thing that bugs me in this equation are these cross terms. So we have d prime A dB, but now here we should have a minus d prime A dB. So this guy cancels this guy. Same here. We have a dA d prime B. That should be cancelled by a dA d prime B. And everything else is just trivially equal to that. So we now check that we have d prime A minus d prime dA times B. So this guy cancels this guy. And the rest cancel. So now we have A times d prime B minus d prime dB. So these two cancel the rest. And we have the algebra of derivations. All right. So the problem is that the algebra of derivations still can be quite large for an algebra. We can produce actually a nice ideal inside of those derivations. So, but this is part of an exercise for you, so I won't do it. But this I'm sure it's in the homework. But inner derivations. So namely, those are of the form add A for A in the algebra G are an ideal inside their G. Actually, this is not hard to check. I mean, it's the same computation we did just here, but it's an ideal in a very precise manner. So this part is not written down in the exercise. But what does it mean to have an ideal? Well, it means that if I just grab a general derivation D instead of a general derivation and an A instead of G, then what I want to do is take the bracket of this guy, which is an inner derivation, with D, and I should get, again, an inner derivation. And it just so happens, so, I mean, if it's an inner derivation, it's going to have to be add of something, and it just so happens that it's add of dA. So this is what people should check. All right, so we've only a few minutes left. So let me just tell you what we'll do next time instead of now. Now let's think of this classification problem. because I didn't tell you about three-dimensional Algebras. So I've mentioned the one-dimensional case. This was abelian. The two-dimensional case. We have two examples. We have abelian, or the algebra that has two generators satisfying this equation. Three-dimensional case. Well, here we have a few examples. Of course, we have the abelian. We also have the example we gave at the beginning of R3 with the cross product as the bracket. And there's a very interesting example called the Heisenberg algebra. So let me introduce what this Lie algebra is. In some sense, we've also seen it, but we've seen it in a different way. Let me give you a representation also of this Lie algebra, so that's why I introduced it. All right, so the Heisenberg Lie algebra it has three generators. So the Heisenberg Lie algebra has three generators. Let me put names to those three: P, Q, and H bar. And the bracket between these guys, and if any physicist is here, he's not going to be happy, but the bracket is just that P with Q is equal to H bar, and any other bracket that I'm not writing is 0. Namely, H bar with P, well, let's just actually write them. H bar with P is equal to H bar with Q is equal to 0. So it's a three-dimensional Lie algebra. H, since H, of course, commutes with H, and it commutes with P, and it commutes with Q, H is in the center, while H bar lives inside of the center of this Lie algebra. Let's call it Heisenberg. Let's prove that this is all the center. So I claim that the center of Heisenberg is just the subspace generated by H bar. I mean, you can prove this in several ways, but let me give a proof that will give us slightly more insight into a general statement. That is, if you have a non-abelian Lie algebra, the center has at least codimension 2. Lemma. On a non-abelian Lie algebra, the center has the dimension of the center of G is less or equal to the dimension of G minus 2. Well, if it's non-abelian, the dimension of this guy cannot be equal to the dimension of this guy. So I need to check that it's not the dimension of this guy minus 1. But if it's non-abelian, there are two non-linearly independent guys, say A and B, such that this bracket is non-zero. But then these two guys are not in the center. So we have a subspace of dimension 2 that is not in Z of G. So the space generated by A and B is not in the center. That's it. So now we have a three-dimensional Lie algebra. It's non-abelian. The center has dimension at most 1, and we found a one-dimensional space inside of it. Good. Let me finish by writing this algebra in a different way. Well, first of all, exercise. Check that this Lie algebra, is isomorphic to the algebra of upper triangular 3x3 matrices. P, Q, H, bar. Probably Q and P should be there. But this is, we called it T3, or N3 before. And let me finish with the following statement. We'll come back to these kind of things all the time, but now that I wrote down the Heisenberg algebra. A central extension of Lie algebras, of a Lie algebra, G is a short exact sequence of Lie algebras where you have 0, say A, let's call it G tilde, into G 0. So this means I have a morphisms of Lie algebras. All these maps are morphisms of Lie algebras. And the fact that it's exact means that the kernel of each arrow is the image of the next one. Actually, the other way around. The kernel of this arrow is the image of the previous one. And the fact that it's a central extension means the following. So what I want is that the image of any element of A in G tilde somehow commutes with the guys in G. So for this we'll talk next time, because now I'm really out of time. But if we pick a splitting of this short exact sequence and we write G tilde as G plus A, then the commutator of any guy in here with any guy in here, I want it to be 0. And this is what happened here. I have a two-dimensional Lie algebra, P and Q. Let's take it to be abelian. And then the Heisenberg algebra is a central extension of a one-dimensional center of a two-dimensional abelian Lie algebra. I'll explain this tomorrow in a better detail. All right, guys. Let's see you tomorrow. Muchísimas gracias.